There's going to be a total of like 3 questions or 4 questions on sig figs. So if I said to you, multiply 4.6, I don't know what I'm typing, 4.56 times 5.678 times 1.2, how would you do that? First thing you would all do is type that into your calculator. I have no idea what the answer is. And you type it into your calculator before rounding anything off. 4.56 times 5.678 times 1.2. Do you all get a 30, a 1, and that there? Now, how do I round off? What are the rules for sig figs for multiplying or dividing? What do you do? So here's what you do. How many sig figs is this first digit? 3. How many sig figs is this? How many sig figs is this? I'm going to go to 2 sig figs, which means this is going to get rounded to 31. Unless that was a 5 or higher, then it would get rounded to 32. This is going to end up being 2 sig figs. Okay? That's the rule for multiplying and dividing, whether it's times or multiply. The rule for adding is what someone else was saying here. So if it says add or subtract, add 12.345, take away, add and take away doesn't make sense. Calculate, calculate, there you go. Calculate that, minus 2.31 plus 6.452. How do you do this one? Again, before you do anything, Christy, you go to your calculator and type it in as is. You don't round off until later. 12.345 minus 2.31 plus 6.452. So I get that there. If it was multiplying, I would say 5 sig figs, 3 sig figs, 4 sig figs, and I would round to 3 sig figs. I would write 16.5 if it was multiplying. The rule for adding and subtracting is you look at the number of decimal places. How many decimal places? 3. How many decimal places? 2. How many decimal places? 3. What's the fewest number of decimal places that I just wrote? I'm going to go to 2 decimal places, which in this case is going to be 16.4 what? Because Germans, yeah, whatever, dumb joke, right? Yeah. What did I say? 16.49, which has 4 sig figs, which happens to be the same as that number there, but not what I asked. It's not how you do it for adding and subtracting. There's also going to be 1 unit conversion question on there. So make sure you're okay with the whole fraction chain. But I want to spend much more of my time looking at forces. I'm going to try and clone some forces questions from the review that I gave you here. And then we'll do special relativity. So, special relativity, we had a review here. Forces, here we go. So, supposing I give you something like this. One of the things we looked at was the famous Atwood machine. That was something that looked like this. If I make it a wee bit bigger. And suppose I said that M1 was 6 kilograms, and suppose I make M2 13.5 kilograms. What could I ask you? I could ask you to find the acceleration, or I could ask you to find the tension. How did we do this? What was our strategy? What was our choice for forces? What was our tool of choice? What was this a job for? We're going to do a free body diagram for calculations. So we said, what are the forces acting on M1? Get the obvious one. And we wrote that as M1G because there's more than one mass, so I'll go M1, M2, M3 as needed. What else? Tension, like you're feeling right now with the silence. And by the way, I should be technical. I called this a free body diagram. Technically, a free body diagram is when you redraw everything and represent the mass with a dot, and you're careful with your arrow lengths. We're actually just labeling the forces on this diagram as a shortcut. Was there anything else on the left-hand side? Isn't there a normal force? Or is there? When is there a normal force? If the object is resting on a surface, or leaning against a wall, which is another example of a surface. Okay. What are the forces acting on M2? Get the obvious one. M2G, and then what did we do? Winner minus loser. We had this tug of war analogy. Our root equation, our starting point was to say the winning force minus, or forces, minus the losing force or forces has to equal ma. That was actually Newton's second law. Newton's second law was F equals ma. Newton's first law was the law of inertia. It was the one that said if the net force is 0, what's your acceleration? If the net force is 0, what's your acceleration? 0, which means you're either at rest or you're going in a straight line at a steady speed. Okay? Or if you know that your acceleration is 0, then the net force must be 0. The other phrase I often said was that means that the forces are, I'm looking for the letter B, balance. That was Newton's first, which allowed us to figure out a lot of missing forces. What was Newton's third law? Often called the action-reaction law, but that's a stupid name for it. Forces come in pairs. You can't have a force on its own. If object A pushes on object B, what does object B do? Push right back with a negative in the opposite direction, but same magnitude as object A. The classic question that I asked you was, in a head-on collision between a big bus and a tiny car, which one experiences the larger force? It's the same. Which one has more damage? The car. Why? Because F equals what? And the car has such a small mass, it's going to undergo a bigger acceleration. You see me once in a while, I wear a t-shirt that says, it's not the fall that kills you, it's the delta V over delta T. It's the acceleration. It's the acceleration that makes the difference. It's not the force. Okay? Anyways, what's my equation going to be here? Who's winning? The heavier mass. So M2, it's going to be M2G minus tension, then what? Plus tension, keep going.
Minus M1G.
Isn't it plus M1? Isn't it in the same direction as M2? Oh, not when you follow it around the rope. When you follow it to the other side, this force does end up pointing up in the loser direction. So it's going to be minus M1G. What's that going to equal? I got to be fussy, not MA. M1 plus M2, or M all, times A. Everybody put your pencils down. Everybody with me. Stretch. Come on. You need it. Come on. Stretch out. Come on. Maggie, you too. Come on. Tristan, you too. Stretch. Come on. Why are we stretching? Oh, love it. If you get to that question, feel free during the final exam to stretch out. Okay? How will I get the A by itself? Come on. How will I get the A by itself? It goes quicker if you call out answers. So we're going to get an acceleration of M2G minus M1G all over M1 plus M2. Get your calculators. We're going to go try going straight to an answer without writing out the numbers. On a test, I would write out the numbers just to be paranoid. Is this a fraction? Is there more than one thing on the top? Yeah. So brackets around the top, and the first mass was M2 was 13.5 times 9.8 minus 6 times 9.8, close bracket, divided by bracket 13.5 plus 6. What was my built-in error check anytime there was a mass hanging from a string? What's the maximum the acceleration can be if I cut the rope? 9.8. So I know it's going to be less than 9.8. Why wasn't it negative 9.8? We said for this unit where you had stuff moving up and down or left and right, we said let positive be whatever's mathematically easiest. You don't have to always say down is negative, up is positive. In fact, here we chose to let down be positive on the right-hand side. What'd you get for the acceleration? 3.77? No, yes? Need some confirmation? Okay. 3.769 meters per second squared. Cool. Sierra, what does B want me to find? Tension canceled. Are you ready? I have a tension deficit disorder because I'm supposed to find tension and there's no tension. I have a deficit of tension. Okay, fine. So how do we do that? Even more general, how did we do that? We looked at one mass. Let's write an equation for one mass. Doesn't matter which one you pick, although often one was easier, but you'll get the same answer for either mass. Emily, would you like me to look at mass 1 or mass 2? I don't care, pick. Mass 1. So now we're going to look at this mass right here. What's our equation for that mass? Who's winning? Who's losing? What's that going to equal? M1A. The other possibility, sometimes tension had a minus in front of it. If tension had a minus in front of it, we did what I nicknamed the swappy dance. We plussed it over and minus something else over. But here, to get tension by itself, this isn't going to be too bad at all. Tension is going to be M1A plus mg, and I'm going to go straight to my calculator in the interest of time. It's going to be M1, answer button, times A plus 6 times 9.8, and I get a tension of 81.4. What are the units for tension? 81.4 newtons. We also had situations where there was friction and stuff like that. Let me find one like that from the review if I can, or else I'll use a diagram and make one up. Show me an Atwood machine hanging over a cliff, Mr. Dewick. That's another Atwood machine. That's boring. Oh, there we go. Now, this question that I took from the review was asking you to find a mass. That I'm not going to be putting on your final exam. So instead, I'm going to say, suppose this mass is 7 kilograms, and let's even, just for giggles, add some friction. Let's say mu is 0.22. And I say to you, find A. You know what this is a job for? What?
Correct. So, do I have more than one mass? Yes, I do. I will call one mass 1 and one mass 2.
What are the forces acting on mass 1, Cole? Get the obvious one. I'll call that M1G. What else? Because it's not sinking in the ground. I'll call it normal force number 1 to go with mass number 1. What else? Which way? How do you know it must be to the left? Which way must this be sliding if it's sliding at all? Yeah, there's nothing that suddenly has masses crawl on their own that way and lifting this up. That's nonsense. So I can use my knowledge of how the world works to say this is accelerating to the right, so friction is pointing to the left. Now, it's possible if I had made this instead of 7 kilograms, 7,000 kilograms, that friction is so big that this isn't enough to move it. That doesn't mean that friction is as big as that. Its friction is only as big as it needs to be. So we'll look at that in a second. What else? Put the cube away. Can you put it on the table over on the other side? Because I know your level of attention and you'll get distracted. Trust me. Like you're feeling right now? Because you want to play with the Rubik's Cube? Mm-hmm. Normal force? No? Okay. What's our equation going to be? Who's winning? Sorry? So it's going to start out as M2G, and then there would be a minus tension. Keep going, Matteo.
Plus tension.
Yep. And we would go, hey, cancel.
Then minus force.
The most common mistake, and I will have this as one of your answers, kids want to do this, don't write this down, is M1G in the same direction as the rope. We're writing the forces along the rope, so don't make that silly mistake. What's it going to equal? Thank you.
Mass 1 plus mass 2.
M all A, or M1 plus M2 times A. Okay? Friction is what times what? So we would go like this. M2G minus mu. I don't know the normal force. Oh, but look. Another force the same size as the normal force. What? M1G. And if I divide that by m1 plus m2, that's the acceleration. Let's see if I can do that here. I think I got all the numbers on my screen right now. So it's going to end up being, is this a fraction? Yeah. Is there more than one thing on the top and on the bottom? Brackets around each. 5 times 9.8 minus 0.22 times 7 times 9.8. Close off the top, divided by bracket 7 plus 5. I guess I could have done that in my head and said 12. I get an acceleration. I know it's going to be less than 9.8 because if I cut the rope on the 5, the fastest it could accelerate would be 9.8. Do you all get 2.825 and then 6 repeating? Anybody else? I need a confirmation from somebody nodding. So 2.83. If instead of find the acceleration, if I instead said find the tension, what would you do now? You would have had to find the acceleration anyhow, but now what would you do?
Do the equation of the mass.
Yeah, and I'd probably do this mass because friction creeps me out. Well, it's just I'm more likely to make a dumb mistake with friction. So I'd go m2g minus tension equals m2a and get the tension by itself. I'd have to do the swappy dance. I'll let you try that on your own or something like that. What else did we look at in forces? We looked at, so there's a couple looking at more than one mass. We did also look at some stuff with just one mass. Huh. My final exam review didn't all print, apparently. I didn't notice that. That's a little irritating. Freeze the screen for a second. Let's try that again. Sorry for the delay, and I'll unfreeze the screen in a second. But let me find what I'm kind of looking for here, if I can. Sure, that'll work. I will give you, a question where the normal force is not equal to mg, where there's a partial vertical or a partial horizontal, so there's another vertical force, an additional force. So this might be an example, something like this. And I'm just going to change the numbers here a little bit. I'm going to make it, instead of 8.5 kilograms, 12.6 kilograms. Instead of 42 newtons, I'm going to make it 51 newtons. You know what? I can make it bigger than that. I'm going to make it 81 newtons. And let's make friction 0.12. Here might be a nice question. What is the minimum force required to make this block accelerate? I guess what they're asking me, what are they asking me to find? What was that? Yeah, we called this one F applied. Okay. What are the forces acting? I'd probably start with the free body diagram. What are the forces acting on this block? Get the obvious one. We have gravity down. What else? Before I do friction, what else? Normal force, bigger, smaller, the same size as mg. As soon as I see another vertical force, I have to be much more careful. I'm telling you the normal force will not be the same size as mg. Why smaller? Because 81 newtons of gravity is being taken up by somebody from off the screen. So I'll really exaggerate it. I'll make the normal force a little there. Now what else? Yeah. Who's winning? F applied? Who's losing? What's that going to equal? More specific. If we just start to accelerate, what we're really saying is we have just overcome everything. We're just starting to accelerate. We're just about to move. We're moving at a constant speed. In fact, you know what? How about instead of accelerate, how about I say move at a constant speed? A is 0 in this case. Or if the previous way I phrased it, I'd be trying to say, how hard do you need to pull just to get it to start to move before you even had a chance to accelerate? In other words, the applied force has to cancel out which force? Look at the picture. Which force? Friction. In fact, what I could really say is, and that's the answer. Except friction is what times what? Mu times the normal force. So I would say, okay, I don't know the normal force. Now, if your test is multiple choice, I guarantee, Nick, one of the answers would use mg as the normal force. But in this case, mg is not the normal force. There's other stuff going on there. Nick, is this mass sinking into the ground like quicksand? Is it flying to like Superman? So if I go really basic, I can say that everything up has to equal everything. What's everything down? Just read it. Yeah, just read it. You said it. What's everything up? That and that. Except instead of and, what mathematical operation am I going to write? Yeah. In other words, if I write a vertical force equation, I have this. mg, everything down, equals 81 plus the normal force, or the normal force plus 81. How would I get the normal force by itself? What will I do with the 81? You are right, sir. It's going to be mg minus 81. So I'm going to go to my calculator really quickly. I'm going to go mg minus 81, and I get a normal force of 42.48. So the normal force is 42.48, and that's going to go over here. Now I can say friction is what times what? Mu times the normal force. Mu times answer button, or answer button times mu. Barely have to pull it all. Why? Because someone's lifting up so much that there isn't much friction. This is why if you're trying to slide heavy furniture around, you can make it a lot easier by lifting up as you also push forwards. Oh, that's way easier. Yes, it is. This is why when you're moving the benches in the gym, if you're sliding the benches and someone comes and sits on it, it gets way tougher because they increase the normal force. So 5.09, you know what? 5.1 newtons. Is that right? Everybody else get that too? Yeah. So there's also going to be some conceptual questions about Newton's laws. Definitely. So questions like, if a car is traveling north and slowing down, which way is the net force? If it's traveling north and slowing down, which way is the unbalanced net force? It's got to be south. Okay. So Newton's laws questions. That's a real quick review of forces. Relativity. That's on the back of your formula sheet, if I recall, yes? Much of this, Oliver, was calculator practice, and this is where I'm going to insist. I want to see every single one of you typing these into your calculator. Joel, no excuses, no just sitting there. And if you don't have a calculator here, you're going to sheepishly borrow one by turning in your smartphone. If you show up for the test without a calculator, I'm making you write the test without a calculator. Not only am I making you write the test without a calculator, I'll probably stand next to you and laugh, my evil villain laugh, while you're writing the test without a calculator, because that, to me, I just have no use for. Don't do that. Special relativity stuff. That was up here, if I recall. There's going to be one, maybe two multiple choice questions about relative velocity. How did you recognize that? Two objects moving at different speeds. No, there isn't two objects moving at different speeds. You pretend one object is standing still and you use the relative speed between the two of them for all of your calculations. What did we say in special relativity our acceleration was always going to be? 0. Took Einstein 10 years to what we did with special relativity, which was always about a constant velocity, wasn't too bad. In fact, we proved it with Pythagoras, you might recall. But it took Einstein 10 years after special relativity to work in acceleration. That's what led to general relativity. In fact, I think I said to you, it shouldn't be called special relativity, it should be called special case relativity. And what's the special case? A is 0. Oh, you want to accelerate? Give me 10 years and some heavy-duty math, and I can work that in too. Oh, and it turns out that also gives us a better explanation for how gravity works. Cool. All right. So, a rabbit is running away at 22 meters per second from a wolf going at 34 meters per second. What's the Oh, my screen is still frozen. Thank you. What's the relative speed between these two at 22 and 34 if they're going in the same direction? I don't care about the positive or negative. What's the relative speed between them? 12. What if they're heading towards each other? What would the relative speed be? 50. Yeah, add them together. What if they're heading away from each other? What would the relative speed be? Folks, who put the cubes away? Also 56. Right? Whether they're going apart at 56 or coming head on or moving in opposite directions, you're going to add them. If they're moving in the same direction, you can go bigger minus smaller, and that gives you the speed direction we can muck around with later. So for questions like trains and things like that, what's the relative speed here in number 4? 12. So we would do something like this. I'll clone this question here. So now let's go relativity. We'll just change the numbers. And yes, that's how I make up your exams sometimes as well. So instead of 8, how about 9? Instead of 4, how about 5? Instead of 415, how about 515? And there, it's a whole new question. And if it asked, how long would it... the question asks, how long until they pass each other? First of all, what's it asking me to find when it says how long? Time. So I would say to myself, t equals question mark. We said for all of these, a is going to be 0. And what that means is typically you're going to be using this equation, Christian. What happened to the half at squared? Because a is 0, and I'm so lazy I didn't even bother putting an initial there. In fact, what I'm going to be used there is the relative speed in this case. Rihanna, when you're done yawning, how to get the t by itself? Yeah. And v is the relative speed. Are they heading towards each other? What's the relative speed then? At 9 and 5, what's the relative speed? 14. If they're heading away from each other, what's the relative speed? 14. If they're heading in the same direction, we would say 5 relative one to another. And you can talk, 4, that's what I said, 4. I said 4. You may have thought you heard 5, but that's because all of you are tired. All of you heard 4! Anyways. You know I control your grade still, right? Just saying. What's the distance for them to completely pass each other? We would say they have to travel that entire distance. The back end of the first train has to pass the back end of the second train. And so the total distance would be 120 plus 515 plus 80. 120 plus 80 is 200, so the total distance is going to be 715. So how long will it take? Try that again. 715 divided by 14. 51.1 seconds. I think I put something like that on your final. I can't remember because I typed it up 2 weeks ago, but I probably would have because in my mind that was one of the things we looked at. And then I put 3 or 4 special relativity. Oh, by the way, your final exam, I labeled the topics so you'll actually see a heading that says special relativity, and you'll know that's where we are. And I'm going to be doing it in the same order that I taught you, except at the very end I put a couple of combination questions that use more than one unit. In other words, the first 3 questions or first 2 questions are going to be sig figs and unit conversion. The next 7 or 8 questions, I'm telling you, are going to be kinematics. D equals VIT plus a half AT squared, VF equals VI plus AT, VF squared equals VI squared plus 2AD, and free fall. Then the next few questions are going to be relativity. Then the next few questions are going to be forces. Then what do we do next? Was it momentum, then energy, and then a couple of projectile questions. Okay? So what would be a relativity question? Something like this. Let's change the time. We'll have it travel for 18 years ship time, and now it's a whole new question. So a spaceship travels at 96% of the speed of light, except we didn't feel like writing out 96% of the speed of light. What does of mean mathematically? Do you remember? No, it doesn't. First of all, what does and usually mean as a mathematical operation? If I say 5 and 4, what will you usually tell me? What's 5 and 4? 9. Usually means add. Why am I saying usually? Because in probability, and means multiply, but that's you'll learn next year. Okay. What does of usually? It means multiply most of the time. In other words, when it's 96% of the speed of light, it's 96% times the speed of light, except we don't do math with a percent. Instead of 96, what would we write? Come on, Math 8. 0.96, right? You don't do math with percentages. You always turn them back into decimals. 96% of something. And if they didn't teach you this in Math 8, it's a handy trick. Whenever I have to find a percent of something, change it to a decimal and multiply. Done. So that's why we wrote 0.96c, but we read that as 96% of the speed of light. Okay, what's this question want me to find? Which time? Look at your special relativity equations. This is the one that has t in it, but I think it also has a t and a t0, or t naught if you're British. Does it not? So, does this ask me to find t or t0? That was really the key. If you understood what was what, then it was just, Tristan, could you type these into your calculator, which was also a challenge. I'll grant you that. So, for the time equation, was t0 back on the Earth, or was... Cole, what? Okay, my stupid way was to say t0 was t on board, and then I just did that in my head. So, this is 18. What do they want me to find then? That. What's the equation for special relativity time? I don't have it memorized. I know it's got a square root of 1 minus v over c. It's got the Lorentz factor that we said. What is it, Jacqueline? It's on your sheet. So you got the t by itself. Did I give you the t by itself in the original, or the t0 by itself? Okay, so t equals, what is it? Which we said, now you're starting to see why we said we can represent it with a gamma. It's easier to write, where gamma is the square root of 1 minus v over c all squared, because that thing showed up in all of the relativity equations. It's called the Lorentz factor, named after a mathematician whose last name was Lorentz. So it's going to be 18 divided by the square root of 1 minus 0.96c over c all squared. Is that correct? Do you see? What do you see? And that's why we often tried to give you the speed as a percentage of light. Now, if we didn't, I would actually type the number in there. And what number would I type in for c? It's on your sheet, I think. 3 times 10 to the 8th. That is the speed of light. That's the cosmic speed limit. That's the speed of light in a vacuum. Nothing, as far as we know, can go faster than that. What about tachyons? They're made-up particles. They're a theoretical construct, but since we can't come up with an experiment to test them, you might as well, instead of saying tachyons, talk about unicorns and butterflies and whatever. It's fine. Nice. Pardon me?
Butterflies are real.
Butterflies are real?
Yeah.
Are they? You sure? Depends what you mean by butterfly.
I don't mean flying butter, I mean insect.
Oh, okay. So, how do I type this in? I advised, until you get good enough, you have a nicer calculator that has multi-line display, it was easier. I started here and worked my way out. I would have said, okay, The C's cancel. I did that by hand. Then I went 0.96 squared. Then I went 1 minus that. Then I said it's the square root of that. And then it's 18 divided by that. So 18 years on the spaceship. If they went away for 9 years, turned around, and came back for 9 years, they would have experienced 18 years. How many years would have elapsed back home on Earth? 64.3. And this is how we found, for example, that it was possible for an astronaut to return home and be younger than his or her child. Right? That was called there's the twin paradox. It was possible for a twin astronaut to go away and come back, and their twin sibling is now way older than them. They're no longer twins, but they are. 64.3. And the abbreviation for years was A for annual. Although if you wrote Y, I'm fine with that. It's just if you're in the U.S., they'll assume you mean yards. I could also give you the time back on the Earth and ask you for the ship time. How would I get the T0 by itself? Multiply that square root function over. Okay. What else was there? We said that as you speed up, time slows down for you relative to the people back at home. What happens to lengths? Let's find one. Oh. Let's try that again. Get that on top, Mr. Duke. Uh, 648 meter long, and let's have it go at 0.93 C. So this answer will be wrong. How long would the observer who was at rest relative to this spaceship measure the spaceship to be? And remember, this had some really neat effects. The fact that there's no such thing as proper length, it meant, and this is reality, we can't tell you how far away any stars are. All we can tell you is how far away the stars are relative to us. But we did a situation where when the spaceship traveled to the star and measured the distance, actually traveling the distance, they got a completely different answer because they were moving relative to the Earth. They found for their universe, for their world, for them, the distance in the direction that they had traveled had actually gotten shorter, and they measured a completely different distance in light years to the star, even though we had measured a different distance in light years to the star, because that's how our universe works. What's the length equation? Anyone? Okay, I'll pick on someone. Chloe, what's the length equation?
Length equals
L equals
L O
L0, L naught, LO, yep.
square root 1 minus the over
That?
squared.
Okay. Did I can't remember, on the green sheet, did I also actually say that gamma equals the square root? So I mentioned that, right? And you know me enough to know I tend to abbreviate. So, okay. What was L0? Which one was it of these lengths? Was it the shorter length or the longer length? I remembered it as the original length at rest, which is a bit of a problem because the time 0 is not the original time at rest. It's the time on board, and it's because of the way Einstein tended to think. He thought everything is relative. And anyways, we're not going to get into that. You'll have to keep that straight. So this question here, are they asking me to find L or L0? They asked me to find L, so it's going to be the original length times the square root of 1 minus 0.93 C over C all squared. Do you see, Christian? Do you see? Do you see? What do you see? And so if I'm going to type this in, I'm going to go 0.93 squared, 1 minus that, square root of that, times 648. So the people on this spaceship, if they ran a tape measure all the way along their spaceship, they would measure their spaceship to be 648 meters long, and that's completely consistent with their frame of reference, with their reference frame. We would measure the spaceship to be 238 meters long. We would, to us, everything would appear contracted. The heights wouldn't have changed. So if we could somehow see the people at that speed, they would look really, really skinny and really, really tall. In fact, one could argue they might look an awful lot like, oh, sorry, that just slipped out. Okay. meters. What else changed in relativity? Masses. Yes? And this mass idea is part of... Oh, I missed a mass question, did I? How much time? How much time? How fast? What length? What length? Mass. There we go. This mass idea, as you speed up, what happens to an object's mass? Yeah, by the way, that's actually not quite correct. If someone here was a relativistic specialist, they would yell at me, because what's really happening is the amount of energy the object uses gets bigger. Put your pencils down, look up. How many of you have seen this equation here? I didn't cover it when we did relativity because we hadn't done energy, but the E stands for energy. What do you think the M stands for? Mass. What do you think the C stands for? If you were to completely nuke someone, and by that I mean transform all of their mass into energy, that's how much energy there is. Who would you like me to nuke? Coal? Okay, everyone pointed at coal. All right, let me pause for a second here. That is a real quick review of forces and relativity. We went over the momentum test a couple of days ago. I'm hoping that kind of jogged your memory, or you can also work on the review. So I'm going to pause here, and you have the remainder of class to work on your final exam review or any other missing assignments. Or if you want to nuke yourself by putting your own mass into that equation in kilograms and finding how much